A very warm welcome to everybody here in the room. So here in Manchester, a warm welcome to the University of Manchester, and a warm welcome to everybody who's joining us online as well. So this is a special seminar as part of the UK's Volcanic and Magmatic Studies Group, or VMSG, 60th anniversary celebrations. So we're a kind of special interest group, so-called, of the Geological Society of London and the UK and Ireland Mineralogical Society. As the title of the seminar series suggests, we're celebrating this year the 60th anniversary of the foundation of this organisation, which I guess essentially exists to provide a community for researchers in the UK, mostly in universities, but also across kind of governmental agencies and some industrial partners too, who are broadly interested in the workings of volcanoes and in magmatic systems. So the VMSG has an annual meeting every year, which is kind of the sort of premier venue for UK and Ireland-based researchers, and increasingly people coming in from further afield as well to share their research. And a particular kind of important part of VMSG sort of operations, if you like, is providing a kind of supportive and collegial community for our students, for our postdocs, and for our kind of junior colleagues. So that's a little bit about VMSG. This event today is kind of jointly held between the University of Manchester, our neighbours at Manchester Metropolitan University, and also the Manchester Geological Association. So very pleased to have all of those organisations participating in this kind of northwest area volcanology event. So my name is Brendan McCormick-Kilbride. I'm a lecturer in earth sciences here in the department. I'm a volcanologist, and essentially all I need to do today is, having welcomed you, is introduce our speakers. The last thing to say for those in the room is that the fire escapes, if we need them, is to go out of this door here at the bottom and take a right turn and just go straight out of the building again. But okay, so on with the seminar. So today we're going to be hearing from two Manchester-based volcanology researchers, and the topic of the overall seminar is satellite observations of global volcanic unrest. So satellites are a really powerful tool for studying volcanoes, the range of different observation types, the range of different data types. And really we're kind of, in many ways, this is a new development in volcanology. We haven't been using satellites for more than a handful of decades. And I think both of our speakers today are really going to show us that we're kind of in a very exciting time for both unlocking these amazing observational data sets, but also really starting to get quite profound insights into volcanological and magmatic processes from them. And I guess our main focus today is going to be monitoring of unrest. So first I'd like to introduce and welcome Dr. Iestyn Barr. He's a reader in physical geography. He's a glaciologist and volcanologist based at Manchester Metropolitan University. He's going to be our second speaker today. And first of all, we're going to hear from Dr. B.Esse, who was a PhD student here in the department and has now stayed here with us as a research associate in volcanology. Ben is going to talk first, followed by Iestyn. I think we'll do questions en masse at the end. So if you have them online, please put them in the chat for now. We can kind of unmute people at the end for a discussion. And obviously, folks in the room, you'll be able to raise your hand and ask questions in the usual way at the end. We'll have a moment or two of chaos as I try to swap the PowerPoints over, but we're going to welcome Ben up to give the first talk. Hello. You have a go at that.
Your lighting options are what we have. That or that.
What do you feel most daunted by, Ben?
That's pretty spooky on the...
I'm happy speaking to a dark room. That's fine. If it's easy to see, that might be better. Okay.
That way? Okay.
Oh, no. Going well already. Cool. Yeah, thank you very much. Thank you, Brendan, for the introduction, and thank you everyone for coming. Yeah, I'm Ben. I'm a postdoctoral researcher here in Manchester, and my sort of Oh, got it all. I'll just try and minimize hide video. Show that up there. There we go. Nice. Yeah, my research is really on monitoring volcanic gases from space. So I'd like to start by saying a big thank you to this long list of names on here, which are sort of our various colleagues and collaborators from within the university and also around the world. Oh, no. I'm too tall. Okay. Yeah, so yeah, a lot of these have contributed to the work I'll be talking about today, and some others from other work as well. But yeah, it's very much been a group effort over the years. So thanks to them. Go back on here. Okay, cool. So. Good. Okay, nice. Yeah, so why do we care about volcanic gases? Well, so volcanoes are really sort of a conduit from underground in the mantle into the atmosphere of these sort of various gases and aerosol species that are vital for life across the world and help sort of build our atmosphere in the early Earth. But they can be quite hazardous as well. Understanding the emission rate and composition of these different gases is great for monitoring and forecasting changes in volcanic activity, as well as understanding the actual magmatic processes that are driving volcanic activity. But also, once these gases are actually in the atmosphere, they can have a really big impact on local air quality. So a lot of these gases can be quite toxic or very unpleasant to breathe in, but also on local or even global climate. And I've sort of shown a nice sort of schematic here is that we can make measurements from the ground in person using aircraft or UAVs or drones, or from satellites as well. And so there's a various sort of range of ways we can tackle this problem. I will say now as well, I will mostly be talking about measuring sulfur dioxide. And the reason for that is that it is not really present in the background atmosphere, but is the third most abundant, typically volcanic gas. So it makes it quite easy to measure remotely. But I will talk about some of the other gases towards the end. So there's this sort of argument about in situ versus remote measurements. This is a nice sort of picture of me sat in the plume volcano, where I was taking some gas samples. And it's not a very pleasant place to be. You can see I've got a gas mask there. I didn't really want to be breathing that stuff in. And it can also be very harmful and corrosive for our instruments that are put in plumes. So sometimes it can be quite dangerous as well. So, and I don't think that jacket has smelt the same since. I think it was about 6 years ago. So sometimes it's better to be a bit further away. So this is a location that we were taking some measurements from at a volcano in Nicaragua called Messiah. And what we can use is we can use special instruments that are able to see the volcanic gases. So here I've overlaid an image of the sort of sulfur dioxide plume coming out of the volcano. And this means that we're not having to sit in that sort of toxic environment, and we can measure from a little bit further away. But sometimes even this is too close. Right? If you have a very large explosive eruption, these can be very hazardous. So here, this is a picture from the eruption La Soufrière in St. Vincent, which I'll talk about later on as well. And these can be very hazardous. Things like pyroclastic flows and ashfall can make it very dangerous to be even not too close to the volcano. But as well, if you have a really dense, thick plume like this, it's actually very difficult to perform these measurements because we're using light that's trying to pass through the plume, and here there's no light passing through the plume, basically. So we're too close to the action in this case. Conversely as well, sometimes the volcanoes are too remote themselves. So this is a volcano called Shishaldin up in Alaska, and it's just really far away, basically, and it's a bit of a pain to get to. So we want to be able to observe and track the changes of volcanoes like this. In particular, these volcanoes are very important, or kind of big impacts on aircraft flying over the Pacific Ocean. So it's really important that we're able to monitor these remotely. And for both these cases, satellites really come into their own. So when we're performing satellite measurements, we're really taking advantage of atmospheric radiation or light. And this is from two main sources. We use visible UV light that's been reflected by the sun off the Earth's surface and then passing through the atmosphere to be measured by our satellite. While the other is using infrared radiation emitted from the Earth's surface itself, then again passes through the atmosphere and then is measured at the top by these different satellites. And you can see, which mouse am I using? This one here. I'll put the little laser pointer thing on. Okay. And you see this sort of orange curve here on the top, and these sort of different three curves here are what we would expect from a black body radiation from the sun on the left and the Earth on the right. And then the filled in parts are basically what's left of the light after it's been absorbed by the typical gases that are in our atmosphere. So things like water vapor, carbon dioxide, ozone, etc. And the gaps, or the areas that we've got left, are basically what are called these atmospheric windows. These are windows in which we have the chance to look for different gases that are of interest to us. And for me, my work is mostly on SO2, and we can, just on the edge of this absorption spectrum here, we can look in this area to measure SO2. So a little bit about the history of these measurements. The first report, or one of the first reports for volcanic SO2 was from the 1982 eruption of El Chichon, from satellites, I should say. We did measure it from the ground before this. What was interesting about this is it wasn't actually a direct measurement of sulfur dioxide, but it was actually a perturbation in the measured ozone. So this is measured by an instrument called the Total Ozone Mapping Spectrometer, or TOMS. And the image on the right there is sort of from the front cover of the issue of Science at the back of the day, which I will point out, it was $2.50. We checked the other day, it's now $15 per journal, per issue, thank you. And what you can see on the image on the bottom there is this sort of map, and the sort of black, red, and yellow colours are an error basically in the ozone measurement that was as a result of the presence of SO2 there that wasn't taken into account by the retrieval algorithm. And this is really useful for us because it means that we've got a whole history of satellites that were launched basically for monitoring global air quality that we can sort of piggyback onto to perform our volcanic measurements. So a bit of a history of all these different satellites. So there's quite a few here, and I've probably missed a couple. So I apologise if anyone's got their favourite satellite that I've missed off, but it does get a bit full, so I couldn't squeeze any more in. So as I said, in the 1980s, we had TOMS, then GOMI or GOME, Skiamaki, Severi, which is an infrared one as opposed to the UV ones and the others, OMI, IASI, again infrared, GOM2, OMPS, TROPOMI, which is what I'll be talking about mostly today. And then also, more recently, we've had two geostationary missions called GEMS and TEMPO, and in the future, we'll be getting Sentinel-4 and Sentinel-5. So we've got this whole suite of different satellite sensors that, as well as the sort of CGI renderings of them have been improving with time, their quality and their sort of sensitivity to gases has also been improving. So a little bit about different sort of orbit types, though. You can split these broadly into two different types. We've got low Earth orbits, where the satellite is sort of wrapping around the Earth or going around the poles and sort of imaging a stripe. And as the Earth moves underneath it, you just progress that stripe along. And this allows you to build up a whole picture of the entire globe on a daily, maybe twice daily sort of basis. Conversely, there's geostationary, which is a much sort of higher altitude orbit, where the satellite is basically moving in sync with the Earth. And this allows it to stare at one single spot all the time. And there's advantages and disadvantages to both, so I'll go through some of these now. So first of all, talking about low Earth orbit data. So this is examples from measured by this instrument called TROPOMI, which I'll be talking about, of the eruption of Fagadacial in 2021. And you can see we're basically getting one image of the plume every day. And it's very changeable. We can see the waxing and waning of volcanic activity from the volcano, which is great. But there's a lot of dynamics within a day that we're not able to capture with this sort of measurement. And then conversely, for geostationary, we're able to stare at one spot all the time. So here, this is a 10-minute resolution, so we're able to see that sort of eruption dynamic that's going on as the eruption is taking place, which would have been completely lost if we'd only had one image for the entire day. But again, there's downsides, and that generally comes because you've got a much higher orbit. You generally sacrifice on your spectral or spatial resolution. So different satellites are good for different sort of applications. As I said, my work is generally focused on using this instrument called TROPOMI, which is this polar orbiting satellite, which gives us daily global coverage. It was launched in 2018, and we've got data from then until present. It's still flying. And what's really cool about TROPOMI is the very high, we'll preface this, it's very high for gas data, a very high spatial resolution of 3.5 by 5.5 kilometers. And this means that we're actually sensitive to, well, across all these different gases, but we are sensitive to sulfur dioxide, even down into the troposphere. And why does the spatial resolution matter? Well, I'll show a sort of comparison with the previous state of the art that we had, which is the ozone monitoring instrument, or OMI. And you can see here that the size of the pixels for TROPOMI are revealing much more detail within a volcanic plume, but also we're increasing our sensitivity. You might just be able to see if you can squint a little bit. There's this little plume coming off to the northwest from the volcano that's completely missed in the OMI imagery. And this is showing some much lower altitude emission that was going on at the same time as this eruption. So got more detail and we're able to get more sensitivity. But this is still just a polar orbiting imager, so we're getting one image a day. We're not able to get higher time resolution than that from the imagery alone. But volcanic processes are happening on much faster timescales. Explosions can be in the matter of seconds or even minutes. So we need something that will delve into this more. And that's where sort of our work comes in. So the University of Manchester Volcanology Group, at least sort of my part of it, we've been developing this tool called PlumeTraj, where we take a satellite image like this, and from each pixel, we launch a series of atmospheric trajectories using a sort of global meteorological models from each of these pixels and sort of see where they're going backwards in time. We launch these at a range of altitudes. So here, light blue is low altitude, dark blue is high altitude. And you can see they spread out because of wind shear in the atmosphere. And basically what we do is we trace each of these trajectories through space and time back to see which ones go back to the vent. And this tells us what altitude the plume is at. It also gives us what altitude it was injected into the atmosphere and what time it was. So we're able to build up maps that look like this as well. So as well as just looking at the amount of SO2 that's there, we're able to produce maps of plume age and plume altitude. And using all this information together, we can then reconstruct a sub-daily SO2 emission rate. So from our single daily image, we're able to look at, in this case, hourly SO2 emission rate. And we can reveal lots of interesting information about this eruption in general. So for this one, we had 2 altitudes of emission that were going on at the same time, which would have been completely missed if we're just looking at the single image by itself. So without further ado, that's enough background stuff. I'd like to get onto a little bit of the science that we do. I'll be talking about 2 eruptions. The first one is that of La Soufrière, which happened in St. Vincent and the Grenadines. And this is an eruption that happened in 2020 and 2021. So a little bit of background about La Soufrière. It has a very long eruptive history. As I said here, about 6 in the last 1,000 years, but there's many more before that. And these can be generally a mix of effusive dome building. So this is where you sort of gently build a lava dome or slowly build a lava dome with time, or explosive eruptions, which are where you have this explosive emission of an ash plume, or sometimes a mixture of both can happen as well. This sort of volcanic activity is extremely deadly, extremely hazardous, sorry. And some of these eruptions have been, unfortunately, deadly in the past, with the worst here on record, at least, in 1902. So it's really important that we're able to monitor these volcanoes and detect any sort of changes in activity. So as I said, this eruption started in 2020 with this effusive dome building phase. And you can see here on the images, this sort of dark blob here was a pre-existing lava dome that was left over from the previous eruption. It was in the 70s. And then as time sort of passed, there was this presence of this new lava dome forming sort of flat slope to the side of the main dome that sort of grew steadily with time. But what was quite interesting about this is that we basically detected no SO2. Very, very minor was detected in situ, but nothing was detectable remotely, either from space or from the ground. And all this went on until April, and then on the 8th of April, it was noted that activity had really picked up at the summit. So the visible sort of degassing from the dome had increased, and we also saw an increase in lava effusion rate, so how fast the lava dome itself was being built. And this is reconstructed really nicely in this data here from Duell et al., where this is reconstructed dome volumes using synthetic aperture radar satellites. And you can see this sort of very nice linear increase in the volume until the very last minute, we have this sudden uptick in the dome growth rate before the explosive phase happened, which is a bit of a spoiler. Coincident with this, though, we were first able to then detect SO2 both from the ground and from satellite, and all of this information wrapped into the alert level locally being raised, and the evacuation order was issued, which is very timely because the next day the eruption went explosive. On the 9th of April, we had this initial explosion, and then there's a couple more pictures though of some of the other explosions that happened over the course of the eruption. And this sort of time series here is showing, in the blue line, I'm plotting the sort of seismic energy release that was going on throughout, and then the orange vertical line, the timing of explosions. So we have this sort of initial explosion here on the 8th, about a 4-hour gap, and then a period of almost constant explosions that sort of then gradually spread out with time until the final one on the 22nd of April. What we're really interested about us from the gas point of view was the start of this eruption, because we had no gas before the lava dome was being built. We saw this sort of precursory emission, and then we wanted to look at the initial phase. So this is what Tropomi saw across the eruption. You can see this sort of SO2 plume that's emitted and then stretches all the way around the globe. You can see there's various other eruptions going on at the same time. I think there's something going on at Piton. There's an Etna explosion as well. So, but we're just focusing really on this sort of main one here. So this is a lot of SO2 that was injected into the atmosphere, and it was transported really quite far. But as I said, we were mostly interested in the sort of initial phase. So we'll go through some of these. So in each of these plots, I'll just go through. Here on the right, we'll have the sort of the SO2 image of the plume, sort of zoomed in, and then we'll gradually get more and more zoomed out as the emissions grow. And then here we've got what we call our emission intensity. So here the darker colours represent there's more SO2 being emitted at that time and at that altitude. So it's like a two-dimensional plot. This is the total SO2 emission rate in red with time. And at the bottom here is this sort of the seismic energy release as well as a reference. So on the 8th of April, we had this sort of precursory degassing that was detected. And it was temporally coincident, so at the same time as this sort of increase in the lava dome growth, as we saw from the SAR data. And also, we had some ground waste measurements of the SO2 emission rates at the same time, which were very much in agreement with ours, so showing that our measurements were really quite accurate. The next day, we captured very nicely this initial explosion, which formed this sort of beautiful hook-shaped plume. But our analysis shows you might be expected to think that this stuff over here is older and this stuff over here is much younger, but our analysis shows that it was actually basically all emitted at the same time in this sort of single violent burst with a very sharp onset, and then it decayed away in the sort of following hours before the overpass. And this is basically bang on coincident with the sharp spike in the seismic release as well. So our timing was pretty good. Slightly wider, it was emitted over a wider time, which is probably partly due to the sort of processes of the plume rising throughout the column. I can answer some more questions about that if people are interested. Then the overpass on the 10th caught this very, very dense plume, which is being emitted at similar sort of altitudes, but basically continuously emitted from these sort of continuous explosions that are going on. And one thing to note here is the changes of scale. So here we're looking at 2. This is now 400, or the peak's at about 300. And now we're at about up to a peak of about 7,000 kilograms per second. So we're going up by an order of magnitude of SO2 release at the same time, at each step. And this is really surprising to us because, as you can see, the injection altitude is about the same. And what we would normally expect for an eruption, for an explosive eruption like this, is for the altitude to scale with the amount of mass that's coming out. So basically, generally, the more mass a volcano is kicking out, the higher the plume will go. What we're showing here is that we're getting 10 times the SO2 release, but it's going to the same altitude. This is kind of surprising. And what this basically suggests is that the magma that was driving this initial explosion that happened initially before the main phase was significantly depleted in sulfur, which kind of follows with what we saw before the eruption when there wasn't any sulfur dioxide being emitted by the lava dome. So using all this sort of information, we're able to build a sort of conceptual model of the eruption mechanism that was going on at the time. So here we have sort of our volcanic edifice. This is my bad cartoon skills, so I apologize for my drawings. But and then we've got our lava dome on top, and then this sort of squiggly stuff is the sort of magma storage region underneath the volcano. And before the eruption, we've got this sort of degassed magma present in the system that's sort of plugged up the conduit. It's not able to move by itself. But as we get fresh magma being injected underneath the volcano, this is then pushing and forcing that old magma out to form this sort of new dome that grew to the side of the previous one. As then this old magma is starting to deplete and the fresh magma is getting closer and closer to the surface, this rapidly increases the dome growth rate, and so we start to see this sort of SO2 emissions. And then after we get that, we sort of have this runaway phase where this initial explosion clears the conduit of the old magma, allowing the main eruption 4 hours later to sort of efficiently erupt the sort of fresh magma that drove the main phase of the eruption. So by combining the Tropomi SO2 imagery with our toolkit plume trad, we're able to sort of reconstruct the SO2 emission history that in much finer detail than we would be able to with just from the images alone. We're able to detect precursory degassing, which is really important for sort of hazard management for eruptions. And we can sort of infer that the initial explosion was very sulfur poor. And all this suggests that the previous dome was built from degassed magma from the previous eruption that was forced out by the arrival of fresh magma. So that was eruption number 1. Now we're going to sort of swap to the side of the Atlantic and talk about the eruption of Tacogaite, which is part of the Cumbre Vieja volcanic ridge on the island of Palma, which is in the Canary Islands, part of Spain. For this eruption, we were a bit more interested instead of being interested at the start of the eruption, we were much more interested about the end. So a little bit about La Palma and Cumbre Vieja in itself is, it's a very interesting volcanic island. It's sort of on the westernmost edge of the Canaries, and it's the site of over half of all the volcanic activity that's happened in historic times within the Canary Islands. This eruption itself happened in 2021 and went from the 19th of September to the 13th of December, and it was highly disruptive. So the lava flow, although luckily there weren't any direct deaths, the lava flows destroyed almost 3,000 buildings and led to the evacuation of about 8,000 people. And this is a very difficult eruption to manage because you displaced a lot of people, and the length of the eruption was very uncertain. So what we were interested here is if we could use the ESSA2 emissions to try and sort of forecast how long the eruption is potentially going to go on for. So this is what the ESSA2 emissions look like after we've run it through our analysis suite. So we have this sort of initial high burst, and then it's sort of jumping about all over the place a little bit, but ramping up slowly until the start of October. We do see this very low emissions on here, which is coincident with this 10-hour pause in activity, which was initially thought to maybe be the end of the eruption, but before it carried on again afterwards. And then what was interesting to us is after this peak in emission, we see this sort of decay with time from the ESSA2 emission rate. And on the bottom here, I'm showing the sort of cumulative ESSA2 emission, so how much has been emitted totally on that day. You see this has got this nice sort of exponentially decaying curve from the trend. So this got our interest, and we thought, well, okay, this has all been done after the fact, but if we had this data at the time during the eruption, would we have been able to sort of project this curve forward with time? So that's what we tried to do. We sort of closed our eyes to the future a little bit, and we just said, okay, well, look, starting from when we start our decay in October and going forward in time steps, and including just that bit of data, what would happen if we then projected it forward in time? So here, we're starting here, and this is up until the 5th of October. The grey line is showing the total curve, the black data here is showing basically the data that we're including in our model. And then the orange line is our fit, our projected fit, and the grey, the sort of orange bars are the uncertainty associated with that fit. What you can see is that initially, we don't have a very good fit. That's fine, we've only got about 10 days worth of data. But as time passes, we start to see a bit of convergence. And on these two graphs here, what I'm going to show is the tau value, which is our sort of the decay rate within our exponential equation up here. So how basically how fast we're decaying away in our emission rates. And on the bottom, we're showing the final emission rate as a percentage of the initial emission rate. So basically, at the end of our eruption, did it stop when we were emitting 10% of the ESSA2 that we were at the start, or 5%? So basically, what point could the eruption no longer sustain that ESSA2 emission rate before it shut off? So for this first bit, we've got about 25 days for our tau value, our decay rate, and about 5% for our final emission rate as a function first. And as we include more and more data, you can see our fit nicely converges, our errors reduce, as you would expect, because we're including more, until we end up with a final decay rate of about 27 days and a final emission rate of about 6% of peak. What's quite interesting about this is that we are, although it wiggles around a little bit, we were consistent throughout the entire eruption. So this would have told us that, okay, we would have been uncertain, we would have been basically right for our forecast of how the eruption was going to progress. Unfortunately, with an exponential decay, as some of you will probably know, exponential decays go on forever. So we don't have a final cutoff date, or a cutoff. We don't have a cutoff point. As I said, it's only this sort of when the eruption is no longer able to sustain it anymore. Our final value is 6% of the peak, but we didn't know that beforehand, so we wouldn't have been able to forecast an eruption end date. But we decided to think, okay, well, if we took a range of these percentage values, how wrong would we have been on a sort of our forecast date? And this is what we're showing here. So we took a range between 2% and 10% of our initial emissions as when the eruption could no longer sort of carry on going. And then this is basically showing how many days out were we in our forecast compared to the actual eruption date. So our 6% one here is bang on because that's what we use. That's what the model said that we got. But you can see that the 2% is quite far out, but between 4 and 10%, we're basically within a month of the actual eruption date throughout the entire thing. So this would have been really valuable information for the sort of emergency managers to have had during the eruption, which meant that I probably should have worked a little bit faster whilst the eruption's going on, but it gives us a nice base for future activity. So to wrap up on this side, so again, by combining Tropomi with plume charge, we were able to get 24/7 monitoring of the S2 emissions throughout the eruption. And we showed that we would have been able to forecast the evolution of the eruption in near real time, if we'd known this ahead of time. And we could potentially apply this to future eruptions. Now, we don't expect all eruptions to have this nice exponential decay. This is quite a nice, well-behaved eruption. But deviations from this sort of exponential model would suggest a change in the eruption dynamics, which would then obviously feed into the eruption response as well. So that's some nice examples of what we looked at before, but what's coming in the future. It's quite an exciting time to be in this sort of world. We've got lots of new satellites that are coming up that are opening up new frontiers for us. So we've got this new constellation of a trio of geostationary satellites. Tempo and GEMS are already flying, and Sentinel-4 should hopefully be launched in the next couple of years, fingers crossed. And all this is opening up or significantly increasing our capacity for really real-time monitoring. So these are all doing hourly measurements as opposed to our daily measurements that we get from our polar orbiting satellites. One thing to note, though, is that you can see that it's very much biased towards the northern hemisphere. We don't have a lot covering the southern hemisphere, which is for sort of geopolitical reasons. So we'd like more of that in the future. We also have more polar orbiting satellites. So in addition to Tropomi, we're having which is flying on a satellite called Sentinel-5 precursor. We also have Sentinel-5s being launched in the next few years as well. And these will provide us with basically more global polar orbiting looks at volcanic SO2. So we're going to have more data in the future. Also, other species are available. I love SO2. This is what I talk about most of the time. But it's a lot of interest to be able to measure other species as well. And we can do this with just with less sensitivity as we can with SO2. So things like hydrogen chloride, bromine oxides, hydrogen sulfide, hydrogen sulfide, and in particular, CO2 is of a lot of interest in terms of capturing eruption precursors. And the launch of the new satellite called CO2M, which would be capable of measuring, well, potentially capable of measuring volcanic SO2, is very exciting. So there's a good handful of satellites that are on the future that will be launched in the near future. So, sort of to wrap up, it's a very quickly moving field, and there's lots of advanced things in sensing technology and analysis techniques that's really opening the doors to be able to peer down into volcanic activity all across the globe. Every eruption is different. Every time we look at a new eruption, we're learning something new, and that's really exciting scientifically, quite hard scientifically as well, but it's great. It's a great field to be in. So it's very exciting. And finally, we've got 50 volcanoes erupting every single day, and we're only just starting to scratch the surface. So I really think with this sort of advance in sensing that they're able to do of volcanic gases globally, that we're going to uncover lots of very interesting volcanological dynamics as well. So thank you very much. Switch over. Straight away. I don't know where I'm going. Oh no. I don't know.
Hi everyone, thanks for coming and thanks for being there online. My name is Iestyn, and I'm going to talk about something slightly different today. Actually, I'm a glaciologist by training, and I've moved to start to look at glaciers and volcanoes together. And I'm going to speak about, as the title says here, whether or not glaciers are helpful when it comes to monitoring volcanoes and maybe even forecasting eruptions. So that's what I'm going to try and speak about. With the last talk in mind, everything I talk about here today is based on satellite remote sensing from non-geostationary satellites, and all the data are freely available from the satellites, at least. So I don't emphasize that enough, perhaps, as I go through, but just to let you know, And there are loads of people I can thank, but I won't for now. I'll move on. So I'm going to talk about glaciers and volcanoes. So I'm going to talk to you about glaciers and volcanoes today. So the talk structure is essentially going to be first an introduction to glaciers and volcanoes and emphasize to you that interactions between them are common. An awful lot of the world's volcanoes have glaciers on them. Normally having a glacier on your volcano is bad news. It normally makes the impacts of the eruption worse. I'll emphasize that point. And it also creates some issues with monitoring the volcano itself. If you cover it with ice, that creates some issues. But what I'm going to try and argue, at least, is I think glaciers might be useful. I think glaciers might actually tell us something about the volcano that they might be sitting on top of. Because they're made of ice, they respond to heating, and various other things that a volcano might be doing. Maybe we should be looking a little more at the glaciers to learn something about the volcanoes. That's the essence of what I'm talking about. So about 20% of the world's active volcanoes have glaciers very close by them. So I go here with a radius of 5 kilometers. So between the volcano, the peak, and a 5 kilometer radius, about 20% of the world's volcanoes have glaciers. And that's what this image shows here. Actually, the orange volcanoes are active volcanoes that essentially have glaciers on top of them, i.e. within 1 kilometer of the summit. The bluish color are ones where the glaciers may be 2.5 kilometers away, up to 2.5 kilometers away. And then the ones in green have a glacier within 5 kilometers. Essentially, the point is there's a lot of glaciers, a lot of volcanoes, about 250 volcanoes globally, that have glaciers close enough to them that those glaciers are likely impacted by what the volcano itself does. Particularly if the volcano either heats dramatically, or even slightly actually, or if it erupts. And we're looking at loads of places around the world. Obvious places would be Alaska, Iceland, parts of Antarctica, South America, and places like Kamchatka and Eastern Russia as well. So we're looking at a lot of places around the world. And these are some infamous volcanoes, really. These are all just a few of the examples of the 250 that are out there of active volcanoes that have glaciers on them in these cases, actually. Everything from Eyjafjallajökull to a place like Erebus in Antarctica and loads of other places around the world. And these are quite infamous eruptions in many cases because of the impact of the eruptions and often tied to what glaciers were doing alongside those eruptions, which I'll emphasize now. So if we think about these volcanoes with glaciers on them, those glaciers normally make things worse, was the point I was making. That's perhaps because they generate floods, i.e. Jökull helps, because ice gets melted during the eruption, or even during a period of heating, and that results in flooding. Those floods can transition into lahars, and you have examples like, not the one shown here actually in the middle, but Nevado del Ruiz, which erupted in 1985, and the lahar itself killed 25,000 people or so. That's because the volcano had glaciers on top of it. But you also have things like fine ash production. As you get eruptions through ice and get really quick cooling, that produces fine ash, which in the case of Eyjafjallajökull contributed to the dispersion of that ash through Europe. My point is, glaciers are making things worse in most of these cases. But glaciers are also a problem if you want to monitor your volcano in the array of other ways that you might do that, either ground-based or remote sensing-based. Most of the things you see in the cartoony image here are made more difficult if you have an example, like here at Eyjafjallajökull in southern Iceland, where you might have hundreds of meters of ice sitting on top of your volcano, trying to determine whether or not you have tilting, for example, is really difficult when the ice itself is melting, flowing, and responding to loads of other things that might be happening. So the point here is glaciers are a problem, and I think most people who study glaciers and volcanoes together, which isn't many of us, consider the glaciers themselves to be a hindrance largely, and should be ignored as much as possible. But I want to try and sell glaciers to you from a volcanological point of view. I think that in examples like this, perhaps the glaciers are telling us something about what the what the volcano is doing. So you can imagine this is an example from Chile. If that volcano starts to move towards an eruptive phase, and as a result of that, let's say starts to heat, that glacier is going to respond to that heating. And that might be over the course of months before an eruption, or maybe years before an eruption. The volcano itself is changing. As a result, the glacier is changing. If we look at the glacier, perhaps we can infer something about the volcano. And that's what all my research is about at the moment. Can we use glaciers to learn something about volcanoes and predict, in particular, try and predict what they might be about to do next? So if you're going to do that, if you're going to look at glaciers to learn something about volcanoes, I think there are three things that you should be interested in. You should be interested in how big your glaciers are. Are your glaciers changing in their size in a way that might be linked to the volcanic activity itself? Is the flow speed of the glacier changing? I'll emphasize this in a moment in the next few slides, but every single glacier on Earth is flowing, hence their erosive power. And the rate at which the glacier flows is not stagnant, like it fluctuates through time, and maybe geothermal heating makes glaciers flow quicker, something I'll emphasize. And then you might also want to look at how the shape of your glaciers are changing. Glaciers are covered in fractures and crevasses, particularly glaciers that sit on volcanoes. Do changes in the surface structure of the glacier tell us something about the ice underneath? Sorry, about the volcano underneath. So what I'm going to talk about today quickly is how glacier size might change and tell us something about a volcano, how glacier speed might change, and how the shape of the glacier itself might change and potentially tell us something about what a volcano is doing. So there's going to be some introductory glaciology, just in case. So let's think first about glacier size. And let's imagine a glacier that isn't sitting on a volcano. This is a normal glacier. Its size is determined by climate. It's obvious, I hope. It's the balance between how much ice builds up throughout a year, which is accumulation, and how much melts away or sublimates away, but essentially how much ice is lost. And if you get more ice build up throughout a year than you have ice loss, your glacier grows. So the size of a glacier and how that changes through time tells us about climate. I hope that's obvious. I think that's obvious. But then what happens, and I also have some bad cartooning ability, what happens if you add, in this case, geothermal heating or volcanic heating, which is what these arrows are showing, to the bed of your glacier? What does that do to the size of the ice mass, independent of what climate is doing, effectively? And this is where some of our research has turned. And actually, what we hypothesize is, actually, if you add geothermal heating or volcanic heating beneath a glacier, your glacier is going to be smaller than it would be if climate alone were determining its size. And therefore, if you heat a volcano up, perhaps your glaciers get smaller and smaller and smaller and are out of climatic equilibrium. And you can look at your glacier and realize this is doing something strange. Maybe it's shrinking much more rapidly than you might expect through global warming. And therefore, it's telling us something about a change in the volcano that it's sitting on. So to test that, to begin with, we looked at South America, actually, and this is a paper that came out last year on this topic. We looked at South America. We looked at 600 glaciers on 37 active volcanoes. That's as many as we could find that had useful data. And we separated our glaciers, so we have 600 of them. We separate them into two categories: those that sit on a volcano, an active volcano, and those that don't. So we're trying to create some sort of control. How big should the glaciers be if the volcanoes are not doing anything to their size? And what we found is for 34 out of these 37 volcanoes, the glaciers on the volcano itself were smaller than the surrounding glaciers, i.e. they are out of climatic equilibrium. They're smaller than we expect them to be if it was climate that was determining how big they are. And this is reflected in their elevation, actually. This is just an example from one volcano. Each dot here represents a glacier. And as we move along the x-axis, we're moving further and further away from the volcano, essentially, up to a distance of about 10 kilometers away. And the y-axis here is essentially the glacier's elevation, so how high the glacier is. And what it shows is as you move away from the volcano, the glaciers are getting bigger and bigger and bigger. Their altitude is decreasing through time. And we're presuming that across this 10-kilometer distance, climate isn't different. They're experiencing the same climate, but the volcano is having an impact on the glacier and making the glaciers smaller. This is one example. We did this for 37, and for 34 of those, we found this trend. So what this, sorry, more recent research that isn't in this paper suggests this is happening globally, actually, for most of the volcanoes that have glaciers on and near them. And what it seems to imply is that the volcanic heating itself is making the glaciers smaller than they would be if it was climate alone that was driving that. And that, I think that's interesting in itself from a glaciological point of view, but from a volcano point of view, what it suggests, to me at least, is if you're monitoring a glacier on a volcano and it starts to shrink at a rate that is disproportionate to the other glaciers around, that suggests the volcano is doing something. So potentially, if you have an example of a volcano that's heating up prior to an eruption, you might find that glaciers are getting smaller and smaller and smaller during that time. So maybe, and this is something we can discuss, the size of the glacier gives us some information about how a volcano might be changing, maybe years to months prior to an eruption, if there's heating taking place over that time. That was my first point. I think glacier size tells us something about what volcanoes are doing, potentially. But we can add to that. We can look at glacier flow speed, so glacier velocity as well. So this is just a cartoony GIF, of a glacier. This happens to be in New Zealand, showing you that glaciers flow, reminding you the ice is constantly flowing. And actually the rate at which that happens, if we look back at it, is not constant, and it's mostly driven by how much water there is underneath the glacier. If you get water underneath your glacier, it lubricates the bed, it creates a separation between the ice and whatever it happens to be sitting on top of, and it allows the ice to flow more quickly. So if you have an example of a cartoon glacier like this, if you get more water under the glacier speeds up. So what happens in this example if we again have volcanic heating? Presumably, if you have a volcano that's warming, it's going to melt more basal ice, therefore create more lubrication at the bed and allow your glaciers to speed up through time. So the second hypothesis here really is if you have an example of a volcano that's gradually heating through time, the glaciers on top of that volcano might be gradually speeding up through time as well as there's more water accumulating at the ice bed interface. I hope this makes sense. And to test that, we looked at as many glaciers as we could around the world. So actually we looked at 85% of the world's glaciers, which is more than 180,000 glaciers, and looked at their velocity, looked at their flow speed for a single year. Luckily, that data, or these data, already exist. There's this paper here that is global glacier velocity, so for every glacier on Earth, for a single year. And we got all that data and separated it into our two categories, essentially. We want to look at the glaciers that are on volcanoes versus every other glacier and see, do glaciers that sit on volcanoes flow more quickly than other glaciers that don't? And we found that glaciers on volcanoes, or near them, within 5 kilometers in this case, flow 50% faster than other glaciers when you look at the global picture. And again, linked to what I was saying before, this seems to apply globally, and it seems to imply that volcanic heating, or the volcano in some way, makes the glacier flow quicker. As I mentioned to you before, I think that almost certainly is due to increased basal lubrication. The volcano itself is melting the ice, which allows the ice to slide around more rapidly, and your glacier velocity increases. So maybe it's the case that if you're looking at an individual volcano and you're monitoring its glaciers, if they start to speed up, and that's building through time, maybe that's an indication that the volcano is doing something. Maybe it's moving into a different phase. And that could happen at least months before an eruption, if not years, potentially. So far we've got glacier size, I think is informative. That might change through time and tell us about something the volcano's doing. Glacier speed, I think, is also informative. And if it changes through time, it's worth paying more attention to your volcano. And the paper relating to this, comes out next week, which is useful. And then the final thing I'm going to speak about is changes in glacier shape. So in a cartoon version of a glacier like this, you have some areas of that glacier that are essentially flat, and you have some areas of the glacier that are fractured. So they have crevasses, and that's essentially determined by how the glacier is flowing, mainly in response to topography. But if a glacier flows over a bedrock dip, it stretches out and you get fractures, you get crevasses forming. But what happens, to come back to my point, what happens when you had some sort of volcanic activity to this? Does it do stuff to the glacier surface that we could then observe? And even if we didn't see, let's say we didn't see an eruption happening or a steam plume emitted, perhaps we can see the impact of that in a glacier anyway. And that is certainly the case. So if you look at many examples from around the world, this is an example on the left-hand side of Four Peak in the US. And this is showing what a volcano can do to a glacier. The surface of that glacier is completely fractured by the eruptive activity in this case. So let's imagine that hadn't been directly observed, but you came to look at your glacier one day and you're like, what has happened to it? Why is it battered like that? You might infer that the volcano has been doing something that we didn't spot. And we could apply that back throughout the observational period of satellites, back into the 1970s potentially. We could go and observe glaciers and see whether they had weird things going on that maybe were related to volcanoes. Another example here from a satellite image shows the surface of a glacier on Eyjafjallajökull, and the arrows here point to big melt pits in the glacier surface. And actually these were formed because water was flowing under the ice. So hot water flowing under the glacier and these big melt pits formed. My point here is seeing what the surface of the glacier is doing. Maybe if we can read that, could tell us something about what's happening to the volcano underneath. And then I think the main example of this actually was in 2009 when Mount Redoubt erupted, and it erupted in March in 2009. And prior to that eruption, 8 months prior, this is what the surface of the glacier looked like. We're looking down on top of the glacier that sits on the top of that volcano. And you can see things that all glaciers have. There are crevasses. All of this area here is crevassed. This is just normal. This is what a glacier looks like as it flows down the side of a volcano. Up in this area here, relatively flat, relatively unfractured. And now we're going to look at an image that's still a month before the eruption. So nothing's happened yet, as far as we know. The same place, and you can see this big ice cauldron has formed here, and it's surrounded by concentric crevasses. And actually, as this paper here tells you, this was the first indication that Mount Redoubt was doing something and was, in this case, about to erupt, although that wasn't necessarily known at the time. So this glacier told us something about this volcano prior to the eruption. So my view is we could look at all of these things. So when volcanoes have impacts on glaciers, they do things like form ice cauldrons, they can make glaciers bulge and fracture, they can lead to widespread crevassing because your glacier might accelerate and stretch out like an accordion and you get this completely fractured surface. So what I think is that if you can observe a glacier and see that these weird things are happening, you know something is imminent. For some reason, your glacier is behaving in a way that you might not expect. So the question is, I guess, are glaciers useful for monitoring volcanoes? And currently my answer is maybe, which isn't particularly helpful, I know. But I think if you have an eruption like this one at Mount Redoubt, and you have a lead into that eruption, and I know this doesn't always happen, as I'll come on to in a second, I think years before you might notice that the glaciers are abnormally small. And that might give you an indication something is happening. Months before, your glaciers might be abnormally quick and maybe speeding up. And I think that tells you something weird is happening. And then just before some form of eruption, maybe your glacier starts to look like it's fractured or has a big melt pit in it or something weird is happening. So I think that glaciers really, really might be useful and informative in these examples, particularly if we combine that with all these other forms of monitoring. So I'm an advocate of glaciers. I genuinely think they could make a contribution to volcano monitoring, and particularly in places like Alaska, where I think this is probably the place to start with applying this technique. So I'll come back to supporting this point in a moment. I think glaciers might be useful, and satellites are the key to that, actually. The satellites are brilliant because we have about 2,500 glaciers globally that fall into the category I was mentioning before, either near an active volcano. We can monitor 2,500 glaciers easily with satellite remote sensing. It allows global scale analysis, mostly automated analysis. You can look at how glacier size is changing almost on a daily basis, velocity certainly on a weekly basis, and how the surface shape is changing if you have good high resolution imagery, again, probably on a daily basis. So I do think this is a real future. where glaciers get monitored for the purpose of volcano observing, really. And this has already started in some ways, which is what these papers are showing here, actually. That's what volcano is that. That's Veniaminov in Alaska, showing the glacier velocity measured from space, and that's continually monitored already, incidentally. So I think now is the time to implement some of this really in an observatory. Just quickly as some caveats, I'm an advocate. There are issues. Not all things that happen to a glacier tell you that an eruption is about to happen. If you look at examples like this, so that's Myrdasjökull, which sits on top of Katla, on the left-hand side there, and this satellite image, and those melt pits you can see in the surface were telling us the volcano was doing something, but the volcano didn't erupt. It's just showing us that there's subglacial melt happening, perhaps because of localized heating. And on the right-hand side here, at Urafjökull in 2017, this melt pit formed in the glacier, and there was some suggestion about, does this mean the volcano is about to erupt for the first time in a few hundred years? But no, it didn't. There was just some increased subglacial heating again. So not everything we see a glacier do tells us that it's about to erupt, which is a problem. Not all eruptions are preceded by heating. And even if they are, it might be super quick or almost unobservable, even through a glacier. But there are plenty of examples where we do get lead-in times to eruptions, as the papers on the left suggest. And the image on the right comes from the lowermost paper there, showing a few examples where there were, these are thermal anomalies, shown in this graph. In the build-up to eruptions, the eruptions are where you get the red star there. In the uppermost example and the lowermost, those are glacial volcanic edifices. So in those examples, we've yet to look, I think the glaciers would have told us already that we were leading towards some phase that might have been ending in an eruption. Final caveat is glaciers and volcanoes are really complex and do weird things. And an example of this actually is in Chile here, where the coloured part of this image is a glacier, and what you're looking at is the velocity of the glacier. But that glacier, Amarillo Glacier, sped up in 2008, a few months prior to a volcanic eruption, which falls into that category. We think it sped up because of heating and therefore lubricated bed, but it wasn't the volcano that it was sitting on that actually erupted. It was a volcano 16 kilometers away, because they've got this linked system. That creates some issues. If I see a glacier speed up, I could say to you, go and monitor that volcano a little more, but then 16 kilometers away might erupt. So there are complexities like that that I think we'll look into. I think they're interesting. So finally, there are more 2,500 glaciers on Earth. I think we should be monitoring specifically for the purpose of volcano monitoring, really. As you get closer to those volcanoes, glacier size decreases, glaciers flow more quickly than you might expect otherwise, and you get weird stuff on the glacier surface, cracks, fractures that might not otherwise exist. So I think monitoring these aspects will help, perhaps with monitoring the volcanoes themselves, because it's really quite easy to look at glaciers. Volcanoes are the difficult bit. Looking at what glaciers are doing is routine, actually. If you want to look at their size, their speed, and their surface shape, that can be done. Obviously, this will be part, if it ever happens, part of some multi-precursor approach. But again, I think, for me, the Alaska Volcano Observatory is the place to start with all of this. But I think it will happen, and I think the time is now, actually. I think it's a cheap and easy way to monitor volcanoes, because glaciers, I think, are telling us something. We just need to learn how to read them. I'm done.
I wonder whether it might be worth having a bit more light down the front. Could you remind me how to turn it back up? Okay, so thank you very much to Ben. Thank you very much to Iestyn for two really exciting and stimulating talks. I'm sure there will be questions in the room and on the chat. So the way we'll do that, please, just raising hands in the room or raising hands in the chat. We may try to unmute people and see if their voices will carry into the room. Failing that, we can put questions in the chat and we'll read them out. But if anybody has a question in the room, they would like to start with that, would be great. And maybe Ben and Iestyn invite you down to the front because I don't need to hear my voice so much as yours. Yeah.
Both really. So lots of what you showed was visual data, or at least pixels in some way of the planet, maybe not our spectral vision. The 2D images of the planet and AI for image recognition is obviously a very hot topic at the moment. So I want to hear both of your feelings on how AI could rise.
Question.
Yeah. Do you want to start? I'll repeat the question and you can go. Yeah, the question was how we can use AI to sort of harness the sort of visual nature of all these sort of satellite imagery.
Yeah, I certainly think in relation to the glacier volcano stuff, it's the way it will go, definitely. And I actually think it might be super rapid. I think within the next year or so, this might be happening anyway. So I definitely think it's the direction, the trajectory. And a lot of this is made for it. There's loads of training data as well. Some of the stuff about surface fracturing is a little more complex, and actually having someone look at those images is really useful. But that might be part of it, and AI is doing the rest. But yeah, I think AI is the future for that.
Yeah, I think from the gas side, there's less available training data because it's probably a more amateur field than the glaciology as a whole, but there is certainly out there. For plume recognition, I think in particular, so identifying images or plumes within the satellite image and tying them to volcanoes, doing that on an automated basis as opposed to just having to identify an eruption going, oh, I'll study that one, probably the best. But then also looking at time series, so not just images, right? Time series are really useful to look at in terms of AI. So if we can look at patterns in the SO2 emission rates, or I guess there's also stuff there, that would be super useful.
About SO2, is the most sulfur emitted fully oxidized? And if it was to react with water from sulfuric acid, does your method pick out the SO2 and take it from the gas?
Yeah. So it depends. So the question was: is most of the sulfur from within the magma emitted as SO2, and what happens when it's converted to H2SO4? Is that So yeah, the first question, it does depend a little bit on the activity style. Generally, for eruptions where you have a much hotter environment, it is mostly as SO2. It's more for like cooler fumarolic fields or like hydrothermal systems, which you'll be getting more H2S. At which point, satellites aren't really your friend for that sort of thing as much. And also, as the conversion to H2SO4 happens, that will be lost from our from the view as well. There are satellites that can look at sulfate in the infrared. It's a lot harder. But what we can do is the timescales of this are typically on the scale of a few hours to days. So you're not using it's not going like that. Bromine's a whole other issue. Bromine does go like that. But for SO2, it's generally okay. And we can also wrap in models of climate or meteorology to try and model that decay rate, although that's hard. But it's an active field of research for sure.
So in your like eruption one, you can see you have like your initial old eruption now in like the 70s or 80s. You've got this cover off, you have an old store of matter underneath. You're saying, well, originally CO2 rich, like SO2 rich.
Mm-hmm.
And that like slowly pass the UV gas in to deplete it, or how is that then lost all its SO2 before the next phase of eruption?
Yeah, cool. So the question was, what happened to all the SO2 from the old dome in St. Vincent? Yeah, that would be my guess, is that because that magma's been sat there for a long time, it's just slowly lost it. It needs to be pretty shallow to start losing its SO2 for the sulfur to come out of solution. I'm going to look at some more geology people to give me depths. Yeah, I think basically just because that's been sat in that system for a couple of decades, it's just slowly off-gassed every time, and so when we bring in the fresh stuff, it's nothing left to go. There was like steam emissions and stuff, so there were still volatiles within the magma, but yeah, probably not a lot of SO2, or at least, sorry, not a lot of sulfur, at least below the detection of it. Yeah.
Oh, that's a question. Oh, we have, do we have one in the chat?
Yeah.
Okay, that's fine. Okay, so this question concerns the comment that other species are available. I understand that hydrogen is difficult to measure. There is much more interest in trying to assess hydrogen emissions from planet Earth. Can satellites help with this? Thank you, Sheena.
Probably not. You can get hydrogen measurements, but typically you need to be in situ because I think the sensitivity to that is too low. And also it'll be very quickly oxidized within the atmosphere. So if you're looking at hydrogen emissions, yeah, I mean, you can measure it with things like Fourier transform infrared spectrometers or using like in situ electrochemical sensors, but I don't think satellites will be useful for that, would be my opinion. But I'm not an expert on hydrogen. So.
Okay, try my luck again. So got a question for Iestyn. How does a changing climate and changes in glacier morphology, flow rate, because of that, which is presumably non-linear as well, how do you kind of correct for that in looking for volcanically induced changes?
Yeah, it's not easy. That's largely why we look at multiple glaciers around a single volcano, a whole region actually, if we can. And we're looking for glaciers that are behaving in some way that's distinct from the other glaciers around them. That's the key bit, really. On the presumption that the others are largely responding to climate. So that's what that's all about, actually. And why we don't just look at the glaciers that are on the volcanoes, because it's hard then to separate their behavior from a number of drivers, actually, including climate, which is the key one. There's interesting stuff about what global climate change and glacier melt is going to mean for volcanoes as well, in terms of future hazards, the nature of eruptions and things like that. But that's the whole can of worms, but an interesting one, definitely.
Thank you.
Question for Iestyn. How do you see INSAR being used to monitor glacial movements over time?
Yeah, it is used and is sorry, yeah. So how is INSAR likely to be used to monitor glacial changes over time? I think it is used, but not widely. Most of the glaciologic community actually look at optical imagery, largely because for things like how big a glacier is or how fast the glacier is flowing, you don't even need good data, really. Glaciers are really slow when they respond to things. So there isn't this big push for that. So if, for example, for a glacier, you just have a single satellite image per month, you can still track changes in velocity. So yeah, it's not widely used, actually, but a little, the answer. And I don't know if that's going to change or not, actually. Optical imagery seems to do a job, I think, so that's what people are using.
I've read that at the end of our time, they try to retreat from Iceland, reduce the waste by so much, some kind of activity.
Yeah.
Is the mass loss of the gases along with the
yeah. So the question was whether, no, the suggestion is that deglaciation of Iceland at the end of the last glacial maximum triggered volcanic activity in some way, and whether or not current ice loss is sufficient to do the same, I guess. And I think the consensus view is it's not completely accepted that deglaciation triggered anything, but it does seem likely. I think the evidence is strong. My understanding is that there's no particular concern in places like Iceland, but West Antarctica is a genuine concern. West Antarctica is a big mass of ice on top of a number of active volcanoes, and there's potential for rapid deglaciation there of a huge body of ice. So I think in most of the world it isn't seen as a particular issue, but in West Antarctica it really might be. The concerns elsewhere are about things like what it means for volcanic hazards if you remove stabilizing ice from a volcano. And that's an interesting area to look at. But yeah, West Antarctica is relevant. Definitely.
Okay. So in eruption series, to try to predict how long the phase of the eruption will carry on, you said your model was mostly in a month. Are you expecting that like to come down? More than from September to December. So a month is actually about a quarter of that time. So quite 20-25% actually. Expecting that to narrow.
Yeah, so the question was, we're looking at the sort of forecasts of eruption end date. A month's quite long, and yeah, you're right. It's better than nothing, for sure, because when the eruption was started, we had no idea how long it was going to, whether it was going to last a week or 6 months. You know, it could have been either. So any handle on that, I think, is very useful, and we do get more accurate with time. I think the big caveat there is that where we landed in that sort of scatter strongly depended on what cutoff we used, as in which percentage cutoff, and why this one ended at 6%, not 8%. We're not sure. We don't know, and that's probably going to change on different volcanic systems. So I think that's probably as good as we can do, given the limitations of what we're doing. And again, this is purely looking at the satellite gas measurements. Wrapping another data, sort of like seismicity, another thing would help narrow that down. It'd be like another, well, as you were saying, another piece of the overall puzzle. But yeah, unfortunately, volcanoes are very tricky things to figure out what to do. But yeah, so I guess yeah, that's my answer. Yes, you're right. A month is a long time, but it's better than nothing.
I don't know if I'll pick up on the mic. I'm just going to come across and butt in. But like this is I think one of the areas where remote sensing can make a really big difference, because we often talk in volcanology about kind of common processes happening in like unique ways. So, you know, for B.Esse, we learn something from every eruption. Like we do. The question then is, how can we apply that knowledge to a different system? And I think this is where the kind of global observations that both our speakers today have been showing us can be really, really useful, because you can start to really drill into how unique or similar are different volcanic systems, and why are the reasons for that, and how does that vary depending on which monitoring stream you look at. So the kind of apparent uniqueness of an eruption might just be because we've never studied an eruption in that way before. And now that we can look at every volcano on Earth at least once a day with multiple instruments, we might be starting to get somewhere in tackling some of those problems, I think.
Yeah, to jump on. Yeah, I think this comes back to the whole AI question as well, because as we get more and more data like this sort of time series analysis, that it's quite difficult for us as humans to look at, might be able to be pulled out by the sort of more machine learning based approaches.
If we're right, would either of you like to say any concluding, closing thing? Want to leave the audience with one last
Not practice that.
It's not no obligation to. Okay, right. So thank you to everybody for joining us today. It's been two great talks. So first of all, let's just thank our speakers again, please. Yeah, thank you to everybody for joining, both in the room and online. This is like one event in a series. So there's going to be another volcanology seminar hosted by UCL next week. And then there's going to be one hosted by the University of Edinburgh and the British Geological Survey in December. So if these are advertised on the VMSG mailing list and on our kind of social. So if people are interested in hearing about those, then feel free to send me an email, and I can put you in contact with the right people if you'd like to listen into those. But otherwise, thank you very much for joining us today. The people who are here in Manchester, this is by no means obligatory, but I was going to suggest we could go next door to Crowbar if anybody would like to get a drink and chat after this. And apologies to people online that we can't extend that invitation to you in the virtual sphere. But otherwise, we do have to vacate the building by 6. So I'm going to thank you all very much again and draw this out to a close.
Is there a question? Or we know? Well,